Everyone, today we're looking at gravitational potential energy, which we usually just do as mgh, but now that we know gravity is a little bit more, it's not just mass times gravitational acceleration. It's a big G, mass 1, mass 2, over their distance of separation squared. That gravitational energy equation is going to be a little bit more difficult. So let's show how we can get gravitational energy for objects in orbit. So we first want to look at is the work done by gravity. And we know that work is our change in potential energy, which is negative force dotted with displacement. Well, what force are we dealing with? What we're dealing with is the gravitational force. So the gravitational force we can simply put in as G, mass 1, mass 2, all over distance squared. And now we're going to integrate the amount of work done while we go across any distance dr in our path. So we'll pull out anything that's constant there. So we can pull out the big G, we can pull out mass 1, mass 2, and we're going to integrate a 1 over r squared dr. Now where are we taking these bounds from? We're going to take it from our initial point, wherever we are in space, to our final point. So when we do this, make sure you don't lose your minus sign. That's a negative gmm over r squared times dr. So when we do the integration here, 1 over r squared should be an easy integral for you. That's going to give you negative r to the negative first power, or negative 1 over r. We're going to evaluate our two bounds with a negative 1 over r. So I'm going to put r final in for my first bound, minus the negative 1 over r for our initial location. And remember, minus and minus is going to give us a plus. So there are my limits of my integration here. I'm going to multiply that by the constant, which is negative g m m, mass 1 and mass 2. But now let's talk about those two bounds and where they are. Your initial r location will be wherever you start in the universe. Say you're starting on the planet. So you're standing here on the planet and you want to calculate your gravitational potential energy. Okay, what about your final location? Where could we go in the universe to have no gravitational potential energy whatsoever? Well, I could get further from Earth, or further, or further, and if I go far enough, way over here, we found it. If we can go infinitely far away, that means that we will have no gravitational energy whatsoever. We won't really interact with that planet whatsoever. So I want you to put infinity in for our final position. And 1 divided by infinity basically makes this whole thing go to 0. So when we do our final setup here and we get our gravitational potential energy, what you get is negative gmm over r. And that's how we calculate gravitational potential energy. Why is it negative? The negative sign doesn't seem to make sense there. But the negative sign means that we're making our 0 point, our no energy location, very far away from us. Think of it as if the roof was our 0 point for every roller coaster problem you ever did with energy. That means every height you'd measure from the roof down would be negative heights, and you'd always have negative gravitational potential energies. In this case, the 0 point, the place where you have no energy, remember, is at infinity. So if you get infinitely far away from an object, as you fall towards that planet, you gain more and more negative gravitational potential energy. I know it's not pretty, but that's just the way we've defined where our 0 point is in space. So here's the curve here. The curve is a negative 1 over r curve for gravitational energy with gmm over r. And as it follows that curve, where we live and what we're usually mainly used to is living on the surface of the Earth and lifting off the surface of the Earth. So when we do that, what we can say is that really right along the tangent line of this gravitational energy curve, that's where you get your mgh. Because we know we're already standing on the edge of the surface, and as we increase our height, our gravitational energy does increase linearly for a while. But if you would stretch that object and lift it all the way out to the moon, the gravitational energy would start to follow this curve. So it's mgh when we're just local here on our planet, But as you get further and further away, you must use the GMM over R. And we didn't even look at the units of that. Let's make sure we understand the units of gravitational potential energy. So the units for big G are newtons, meters squared per kilogram squared. The masses are kilograms times kilograms, or kilograms squared. And now we're just dividing by R, which is meters. We don't have to square this time because we're not dealing with force. And when we start canceling things, we can see that one of the meters goes away and both of the kilograms go away, which leaves us our Newton meter, which means that gravitational energy is measured in joules. So we can do the energy just like we've done all other types of energy, but now remember it's a negative type of energy because of where we put our 0 point. So there we are. We've got a rocket on Earth. Earth has mass m and the rocket has mass, we'll say, little m. So when we want to look at this, we can say, all right, how high would our object go? What is the maximum amount of height we could possibly get? Well, we want to conserve energy like we've always done. So you can do this through LOLs or just write out energy equations. My starting energy here would be gravitational potential energy. Negative gravitational potential energy. Why? Because I see a mass, I see another mass, and we are a distance apart. We are the radius of the planet apart right now. So if we have them a radius distance apart, we know we have negative gravitational. So now we take off, we burn our fuel, and off goes the rocket. The rocket reaches its highest point right here, going straight up, and when we reach our highest point, we know we're going to stop. So at the highest point, we're going to have gravitational potential energy. Why do I know that? Because now I'm a bigger r distance away. But we did forget an energy in the beginning there. We forgot our kinetic energy. So when we take off from the surface, we've got negative gravitational potential and we've got kinetic energy due to our engine and our thrusters. When we get to our highest point, we are going to stop, so we're going to have a new gravitational potential energy at our highest point. So if I want to solve for how high could I possibly go, this is our original height and this is our final height. So let's set this up. It's going to be negative g, mass of planet, mass of rocket, over initial height, plus kinetic energy for rockets in space is no different. It's still 1/2 mv squared, thank goodness. And then this is negative gmm over your final position. So I've been trying to solve for my final height here. I've got to get everything away from RF. And if I'm looking for RF, I need to get rid of the G. So I'm going to divide that over and get rid of G and the two masses. Over here, I can get rid of the mass of the rocket and leave the mass of the planet and big G behind. So big G, mass of... So everything now has been divided over. It was divided over by a negative, so we'll make everything opposite signs, which leaves you just 1 over final position. So if I want to get my final position, I'm just going to flip this side. That means I have to go flip everything on this side. So it's going to be my initial position minus gm over 1/2 v squared equals my final position. Now, if that position wants to know just really how high above the surface of the planet, what you're about to solve for here is this total RF over here. If you want to know how high you are from the surface of the planet, remember you have to subtract the radius of the planet so that you don't include that in your height equation. You could also figure out how fast you'd have to go to get to this new height based on using just energy conservation. But what if we wanted to go faster? So looking at Newton's cannon here again, if you fire faster and faster, eventually you fall around the Earth and never hit it. And that's what orbit is. But could you fire faster? It looks like there's bigger and bigger rings out here. And there is a minimum velocity that we can attain where we can break free of Earth's gravity and escape the planet. And we do need to know this because when we want to send satellites out into deep space, we not only have to break Earth's gravity, but if we try to send that spacecraft towards other planets, we don't want it to get stuck in that planet's gravitational field, unless that's the planet we're trying to study. So we do need to know escape velocities for every single planet. So if we want to escape a planet's gravity, we have to look at all the energy, all the kinetic and all the potential at all locations. So we set up conservation, say that our initial kinetic to take off the planet plus our initial gravitational energy, which remember is negative, equals our final kinetic and our final gravitational potential. Well, if we want to escape Earth's gravity, we want to get somewhere where that potential energy curve goes almost to zero. So that means we're getting infinitely far away from the planet. And if that's the case, then we could say final gravitational energy goes to zero at infinity. Now what would happen to your speed? Well, when you reach your highest point, and you've reached that point of infinity, you've actually stopped moving. So that means your kinetic at the end goes to zero because we're no longer moving at that point. So what does that mean now? What that means is, that means that 0 equals 1/2 mv squared minus g mm over r. And if that's the case, then we can just solve for velocity, the initial velocity we need to leave and escape our planet. And so when you do that, you get gmm over r equals 1/2 mv squared. What mass are we talking about here that has kinetic energy? This is the rocket's mass. And over here, this is the mass of the planet and the mass of the rocket. So let's get rid of the rocket's mass again. Solving for velocity, what you're going to do for velocity is move the 2 over and square root. Escape velocity is 2 times the gravitation constant multiplied by the mass of the planet all over the radius of the planet. And now you know how fast you have to go to escape. If you go less than this escape speed, you'll reach your highest point and just fall back down. And if you go faster than this escape speed, you will break through Earth's gravity and leave the planet. So if you do this for Earth, you put in all your values for Earth, g, the mass of Earth, the radius of Earth, and do your calculations, you'll get around 11.2 kilometers per second to escape Earth, which again, kilometers per second may not mean much to you, so put that back into miles per second. It's around 7 miles each second. So if you can travel around 7 miles a second, you now escape Earth's gravity and you don't return. 5 miles a second was how fast you had to go to orbit the planet, but 7 miles a second is how fast you have to go to actually leave it. So it's only 2 more miles per second, which now means 28 laps around the track every single second. Pretty fast. So it brings us back to one last point here, the binding energy. When astronomers look out at different things in space and watch them orbit, what they try to see is if they have enough binding energy to stay with their host mass, whatever that host mass is, say the Earth or Venus going around the Sun. Looking at our gravitational energy plus our kinetic energy, if you add those two things together, if they are less than 0, then the planet is bound to its solar system. If that total energy is equal to 0 or greater, then you are unbound and you will leave the solar system. Earth is moving with a velocity of about 30 kilometers per second. It wants to go in a straight line away from the Sun. So we know the mass of Earth. We can do 1/2 mv squared and get the kinetic energy of the Earth going around the Sun. It's going to be a huge number. But when you add that to negative g, mass of Earth, mass of Sun, over the distance between the Earth and the Sun, you combine the kinetic energy and the potential energy, you'll end up with a bound system for the Earth and the Sun. You get a negative amount of binding energy. But there are objects that do have binding energies that are equal to 0 or greater than 0. And those things are like comets that come on very hyperbolic planes. They zipping around the Sun, and when astronomers look at these comets as they come hurtling towards the Sun and start to melt, as they look at the comet, they figure out the mass of the comet, they figure out the gravitational energy, but then they also figure out the speed that that comet is whipping around the Sun. And when they calculate those, if that comet's energy is greater than 1, that's an unbound comet. The comet will sweep in and leave and never return to our solar system. An example of a bound comet is one that comes back to us every 76 years, and that's Halley's Comet. So Halley's Comet swoops in to our solar system every 76 years, melts, and then swings way back out here and freezes again. And when we calculated the binding energy of Halley's Comet as it went around the sun, the gravitational energy plus the kinetic energy means that Halley is stuck. Halley is not going anywhere. It's going to stay with us, and it'll be back every 76 years. So it was last here in 1986, so it'll be back in 76 years. Figure out how old you're going to be when Halley's Comet returns. And actually what that'll tell you is exactly where Halley is in its orbit right now. Half of 76 is around. In 38 years, Halley will be at its furthest point from the sun. So that means that after it gets to its furthest point, 38 years later, it will return back to us. So that's an example of a bound versus an unbound energy when focusing on objects in our universe.